The lecture has been organized in a sense that I will briefly cover the challenges that represent to detect nanoparticles in the field, why they are so challenging. I will be covering some of the features of the Astrios that allow this capacity to resolve nanoparticles to happen. Some of the work that we have done on sensitivity evaluation on the Astrios at the University of Melbourne to understand the instruments that we have and how we have characterized these. And then I will be covering a 3-stage procedure that we follow to progressively arrive to this nanoparticle resolution. Finally, I will be covering some interesting results that I cannot still make sense of completely, but suggests that the Astrios at this level of resolution will start making hybrids between the noise and the nanoparticle pulses. So it gives you a kind of understanding of the relative value of high measurements, area measurements, and pulse width when you're dealing with these very small intensities, yeah, near the background. So there is a limit of detection in cytometry, which most instruments share. Most instruments will stop very close to 200 nanometers. And some instruments like the Cytoflex, and not only the Cytoflex, but all instruments can get down to 100 nanometers. And we saw last year in the Cytoprac that using the Cytoflex technology, it might be possible to get down to even smaller numbers. Now, this would appear as whatever, the result of the technology the development, but there is an actual massive challenge in going anywhere from 200 to 100. And that's the reason why 200 is the limit. Clearly, exosomes have been triggered in the whole development. I'm not an expert on exosomes, by the way, so, but I'm interested in sensitivity evaluation. No, when you consider the field of nanoparticle detection and exosomes and extracellular vesicles, you are essentially working at the limit of detection of any instrument. At this level of detection, you will start facing and finding things that you would not see otherwise when you're working with traditional samples and cells. So all of this is derived from the fact that there is very limited volume and very limited size in the nanoparticles that you're trying to evaluate, so you don't have many epitopes to actually put fluorochromos on. The scatter itself is a challenge because at this level of sizes, you don't have linearity, so half the size doesn't mean half the scatter. And then you have a lot of effects that are background related, so from free-floating dyes to nanoparticle contaminants and sheath-borne particles, all these will affect and will compromise your resolution. There is also the issue with droplet discrimination. We use a lot to distinguish a single from double particles is the fact that these particles are so tiny that the pulse width measurements are actually not a reflection of the size. And you get all the effects, which are like swarm detection and increases the amount of noise. And due to all these reasons, fluorescent is usually favored. I mean, between fluorescent and scattered, fluorescent have the advantage that you can cut out the noise quite substantially. If you have bright dyes and good methods, you can see nanoparticles triggering in fluorescent, but scattered is usually avoided. And the reason for this is what I was mentioning before, the nonlinearity of scatter dependency with size. For instance, if you go down to from 200 nanometers to 100 nanometers in this scale, so this is an angular representation of scatter after you have excited a particle of different sizes with 160 milliwatts of 488, and you are talking about a flat top, roughly of 15 to 16 microns. You see that from 200 to 100, there is a jump of 100-fold. So from 100 down to 80, 60, and so on, you get variations, of course, limited and smaller scatter, but it's not that massive jump. That had to do with the laser that you're using, clearly, 488, and the relationship of the wavelength to the size of the particle. But this is a basic reason, the main reason why most instruments cannot go beyond 200. Now, we consider scatter the same way we would consider fluorescence. So scatter deals with waves, and there are many things that are actually not captured by the photons that you count, but at the end it's a photon counting procedure. So you're measuring photons and the detectors. So there are many things that are shared with fluorescence and what actually makes fluorescence sensitivity or not. But there are things that are specifically complicated when you deal with scatter. And many of these elements that I'm mentioning here actually are all overlapping. So if you look at scatter magnitude and the relationship with size, you're also talking about the optics that had to be specially designed to collect the angles that you're producing. You have the quantum efficiency, of course, how efficient your optics are to collect all these photons, or the little photons that you're getting. And you get, of course, background all over. The other thing that you have is electronics. So you need to have a powerful electronic system that's able to characterize subtle variations in intensity that these nanoparticles will have. And the Astrios is one of these instruments. I can say that based on the features that you have and you can access in the brochure, there are many things in the Astrios that are meant to help you to find a better way to handle scatter. So you have a small particle detector in the forward scatter, which is fully customizable. So you can get 2 forward scatter measurements and you can adjust things like masks. It collects light in a 45-degree angle, which essentially follow what happens when you go from towards smaller sizes. The scatter tends to be less forward and more also sideward. So there is no that distinction between forward and side scatter that you see in bigger particles. We also have a 40 nanometer inline sheath filter. So in principle, nothing that is nothing over 40 nanometers can pass and get essentially to the laser. Our lasers are typical lasers, 200 milliwatts for the 488, 561, 100 for the 640. The lasers are delivered via fiber, so you get kind of stability in the precision, in the pointing stability of the lasers. And we also have an additional optical kit box that looks really slick. They have all set of filters, band passes, and masks, so you can customize your instrument and do whatever you want. You can treat it in any laser. You can collect small and large particles simultaneously. All of this due to the small particle detector assembly. And it also have 100 megahertz of sampling rate and a 32-bit acquisition system that allows you to measure really subtle variations in intensity. Now we got 2 at the University of Melbourne, and I will refer to these instruments at DS or PDI, Peter Doherty or Dental School. The forward scatter is interesting that you have this assembly that looks a little bit like a Star Wars ship. You can measure 2 scatters if you want, 2 forward scatters. In the middle here, I cannot point, but you can host a 50-50 splitter. So you can split the forward scatter in 2, directed to different PNTs, and on the way you use masks and ND filters and band passes, so you can see, for instance, macrophages and bacteria easily. Yeah. The masks look like this. I'm assuming they clearly went through a lot of predictions before they actually decided this was the masks that were enough. And we, as I will show you later, we use the mask a lot to essentially improve the forward scatter detection. Now, these are all the elements that actually we access. So when we're trying to get the instrument to detect nanoparticles, we want to consider all the factors that would impact on the resolution. And in the study that we've done, we have been playing with things like the laser power, the triggering laser, the density of the laser at the interrogation point. We play with different particles, different materials, most of them NIST traceable. And we play a lot with alignment. I mean, most of the work is alignment based, and of course you play with the mask and the detector gains. So all of this will have an impact in your resolution. Now, in 2016, we carry up, I call it refurbishment, but it was actually a fine-tuning of the capacities of the Astrios. In that case, we were concerned and we were thinking that maybe we were losing some power. Our measurements were not as good at the interrogation point. So with the help with OC engineers, we spent like 2 days going step by step from the laser head down to the interrogation point. And the goal of the exercise was to maximize the output power. So we ended up with these powers, which is the ones that I'm assuming I still have, and they are representing 20% loss. But we essentially find things like we reassign fibers, we remove ND filters, we try to remove anything that could cut down the light a little more. Yeah. Now, out of this work, we went from a resolution that was not actually so good down here to a resolution that was actually astonishing. So people tend to think that getting airs by default will have less sensitivity than a cuvette, sort of like the ARIA or the Fusion. But my experience working with this instrument for like over a decade is that the instruments can be as sensitive or more sensitive sometimes than the cuvette systems. It had to do a lot of background. I will not get into details, but we can discuss this after. But essentially, we went to the case in which we managed to actually get the instrument at the levels of the MorphoXCP and a level that will match competitors. This is a before and after resolution that we're getting in FitCMP, just to give you an idea of how that looks like in terms of profiles. And we also did some kind of work trying to match the instruments, making as consistent as we can. We have a platform that have like 35 instruments. We want our instruments to be actually at the best possible performance. And we also did some other work. This is a little busy. So if you're like the Astrios, at least our Astrios, you get a kind of feeling that you don't get a correlation between the optimals that you get for each laser. That's for our instruments. And we try to study how much of a correlation you have actually into the optimal focal point for different lasers and different measurements. So what I did in this case was we were scanning and essentially scanning the BSO. We were taking the BSO closer. The BSO is the one that will take the laser's focus to the jet. We move it back and forth around the optimal that we have, and we measure the resolution index at each position, trying to see how all the measurements will collide and how much correlation we have. And we found that some lasers are correlating, like for instance, if you look at the yellow-green here, and the FITSI detector, the blue path, you get a nice correlation, so you get the optimal for both. In other cases, we don't have that correlation. So we took that into account when we were doing the nanoparticle study, because we knew that in our case, blue scatter would be awesome, yellow-green would work fine, violet sometimes, depending on the instrument, might not be a good choice. We also know that there are different sensitivities in the instruments. Some of them are more powerful in the blue path, some more powerful in the violet path, which might explain the results that we're getting. So that signal, trying to maximize the signal, that's a very important thing. But something that we ignore because we usually move completely away from that realm is background and what background can do to your signals. Now, I put this example because I think it's a perfect example for everyone to understand how important actually background is. So you have powerful eyes, you can see the Milky Way, but if you're in the center of the city, you won't see nothing. If you grew up in a place with a light pollution, you might not even know that there were stars. You would never find any guidance to any place. And what it means is that with the same sensitivity, the same powerful detectors, you might be ignoring particles down the low end. And the background in that case will become the dominant factor. That happens for fluorescence, that happens with scatter. No matter how powerful you are, if you don't control your background, you will see nothing. And when you think about background and jet inerts, clearly the typical view is that jet inerts will be intrinsically noisy, because you have jet formation, you have droplet formation, you have all the scatter that you can measure easily if you essentially look for it. Now, this is one view, clearly. That's a view that I also share for many years. But when you look at the flow cell of the Astros, or any flow jet inert cell sorter for that matter, you will see that the light is mostly focused around the plane where the laser is coming. And the remainder area is kind of dark. You can control that. You can see the patterns. You can see interference patterns. You can see the forward scatter main component. You can see all the interference. You can predict that pattern. That's what I mean. It's a predictable noise. It's controlling space. It's geometrically contained. If you look at a flow cuvette instrument, sometimes, at least in the instruments that I have, you can see the light scatter going all the way and everywhere in the flow cell. So that is essentially like the equivalent of trying to measure things in a disco party or the center of the city. Well, for me, a jet actually is the minimum volume that Cytometry can offer. It's a 70 micron, self-renewing, beautifully clean, laminar jet, no other interference, zero background, or very little background. Yeah? Now, in order to do this procedure, and if you guys have done ever something like chromosome sorting or alignment for chromosome sorting, you will realize that anything that you know in terms of alignment and optimization when it comes to big particles would not apply to actually the critical cases like chromosome aligning or small particle alignment. So we went really slowly and cautiously, following three main steps. So the first time I would call the coarse alignment step, that essentially is following all the procedures that Berman Coulter would tell you should follow to make sure the jet is laminar, there is no turbulence, the alignment is optimal. And that is done with the QC bits, the 3.4 micron bits. The second step is a little more tedious because you are now, in this case, are trying to deal with a kind of battle between the noise and the signal. You want to make sure that your signal to noise ratio is maximum. And I'm using a bit that is on the edge at 200 nanometers, yeah? The boundary between what you can see and what you cannot. And in all the cases, what I'm doing is actually considering the noise as it was a dim particle. I'm looking at the resolution between the noise and the signal all the time to know how far I have gone in terms of landmarks and alignment. And the last one, which is also important, is I wanted to know how many particles could I fit between 200 and the noise. And that's essentially how it worked. In that case, you will also require a very tiny amount of alignment, but it's actually minimum. So the initial one, the core step, will essentially cover everything. If you have worked with the Astros, you know what I'm talking about. It's all the setup procedure, everything that is optimal, like everything is fixed, everything is laminar, no turbulence, no noise. Our QCs are actually really good. We get normally like 1 or 2 CV in terms of the peaks that we get for the QC report, and we do the whole thing, like droplet generation, optimal frequencies, drop drive volts, time delay. Now we are essentially tackling everything that is kind of coarse. Stability of the laser, illumination, stability, turbulence, everything that we know, we need to be there first before we actually can go any deeper. The second step is what I call nanoscatter step. Depending on how you do it or how many different days that we have tried this, we can do down to up to 20 steps actually of individual alignment and repositioning of things. But the most important thing and the crucial thing, as I said, is that we don't cut down the noise. We want to see the noise, and we want to see roughly like 30% of the noise. So we're essentially tackling and adding all these elements that I'm here, so the BSO, the jet, and the forward scatter assembly, playing with the mask, trying to slowly get there. And of course, in the forward scatter, we simplify the system, so we remove the beam splitter, we remove the mask and the ND filter. We want to get everything that we can get with a single detector. And this is an example of one of these procedures. So I have done this many times, and every time we'll be essentially trying to, after anything that we do, we save a file to see how it takes and how many things affect the measurement. But when you start with the Astrios and try to see 200 nanometers in the first one to the left, and you're using 15 volts of drop amplitude for the droplet generation, and you're talking about a massive amount of noise. In this case, we were getting 200 kilohertz. We know that was noise that was drop related, and we took essentially the amplitude down to 5. So you don't need to start with 15 volts. You can go down to 5. You can find the optimal voltage that will minimize the noise at the interrogation point. Then we essentially started finding, well, we wanted to know if this was noise or particles. We took that the threshold until we find the noise. You can see where the noise appears by increasing the EPS. So we keep essentially the threshold down all the time to follow the noise at every step of alignment. Yep. And you see the effect, for instance, of sample differential pressure, no effect in that case. We remove the beam splitter and the ND filter for the forward scatter, no major change in the forward scatter. The major effect here was actually the realignment of the jet. Yeah, so I'm talking about an instrument that went through the QC procedure and passed the QC all fine. Yeah, and you get a massive increase in the size scatter in this case, and the second landmark, as I can say, is that the actual position of the BSO. So by playing with the jet to the BSO position, we managed to get something that is very close to 100-fold in terms of size scatter resolution of 200. And after that, what we do essentially, we play with the mask to try to improve the forward scatter. Eventually, you can use any of these masks that are here, but that will give you something like this. Yeah, you get a 2 log decay difference between the 200 nanometer particle and the noise, and below 2 log decays between the forward scatter of the 200 nanometer particles and the noise, which was our aim. Now the question is, what can you fit in between that? The other thing we did was to find the optimal gain. So the gains on PNT gains and PNT voltages have a massive effect in reducing the stochastic, the randomness of the measurement and the error in the measurement. And we did a voltration the same way you would do with fluorescence. So we used the 200 nanometer particles and the noise, and visually and also mathematically calculated a value of stain index. So as you increase the gain, the volts in the PMT, you see, of course, you see the decrease in the CVs of both the 200 and the noise, and you see an increase in stain index. So in our case, you will say that the optimal gain will be around 350 or 400 volts. Now, the other important thing about this comes from the theory of sensitivity. So people know that the optimal value of PMT in terms of voltage is inversely proportionally to the amount of signal that you started with. So rainbow beats, if you organize rainbow beats from 8 to 2, and you do a voltration and see how the CVs behave, you see that the CVs of the brightest beats minimize really quickly. Yeah? The CVs of the dimmer peak will take longer. So the bigger the CV, the lower the signal, the larger the optimal PMT, the lower the signal. And if you apply that to this, the conclusion is kind of strong. Like the 200 nanometer beats at this point of alignment are acquired so efficiently that there is almost no effect of the PMT. They reach the minimum really quickly, as a bright peak will do. And the noise takes longer, less photons. So we are controlling the photon noise down to a level that is Poissonian. Yeah? So this is actually very striking. There is very little noise in the Astrios when you get to this level of resolution. Now, the other surprising things, and I have to repeat this again, is how much crosstalk you have. How much another laser can interfere with the measurement that you're doing in the 48 path. Yeah? And in that case, what we did was first, we don't provoke the monster. We don't use optimal frequencies many times. Sometimes we do, and then we take down the amplitude. Or we use what we essentially, people that work in the getting energy sorters know as quiet frequencies. These are frequencies that are not very far from the optimal, but they decrease massively the level of oscillation that you get at the interrogation point. And with these kind of settings, we went from removing the forward scatter altogether with all the lasers on to having the optimal configuration. Essentially, there is no difference. So you can remove the forward scatter bandpass filter and you still don't get any influence of any wavelength whatsoever in the measurements that you're doing. I don't know how the Astro does it, but that's essentially what we got. The other interesting thing that happened when we're doing the alignment, when you look back to the data, we're trying to find different things that you could get out of the data that we were generating. It's something really interesting. Is that the Astros, when you get to the optimal level of alignment, can resolve nanoparticles from noise based on pulse width signatures. So in this case, what you have is kind of a heat map. The color represents the width of the side scatter high pulses, yeah? So as you go high, essentially in the width, you will get into red, orange. Nanoparticles will essentially reside at the bottom level in terms of pulse width. Minimum pulse width, completely resolved from the noise. And you will see also the rendering, like noise tend to be larger width, particles will be essentially at that minimum. And if you see the progression of the alignment that I showed you before, and how the width of the signals and the pulses behave, you see some contamination of the kind of intensity and the pulses of the noise into the particles. But as you progress and you go down to the optimal resolution, you get this beautiful resolution that is not only in terms of intensity but also in terms of width capturing. And that is actually really interesting, because if you can capture the nanoparticles based on the width, you can use that to purify your measurements out of noise. Yeah. The last step was essentially using nanoparticles below 200. And we used for that case a prototype mix of beats that Cytoflex is working on. It's a prototype that go down to 80. These are NIST particles, and we actually use the Apogee beats. And these are the beats that we're using. Some of them are fluorescent, so we can tell that we're measuring actually 110 based on fluorescent measurements. So this is the raw, after the alignment that we did, this is what you get out of the Cytoflex mix in the instrument. Yeah, unfiltered, unscattered, everything. You can even see sometimes, like in that case, you see a kind of electronic noise signature, a very kind of like a current kind of signal that doesn't make any sense. If you look at the width, you see essentially a kind of splitting of the nanoparticle. You got some components that come clearly from the noise in the absence of any particles in the width, and nanoparticles will all reside down at the bottom end. Something really interesting is that you don't get distinction in terms of pulse width in nanoparticles that are below 500 nanometers. The instrument cannot tell, based on pulse width, as you do with larger cells, the size of the cells based on the pulse width. These particles are so tiny that compared to the laser waste, the size is negligible. So the width actually becomes a function of the velocity of the jet and the waste of the laser. In the fluorescent side, you will see where the background essentially is located, and you can see that you have 100, 110, 100 fluorescing or not fluorescing, and then you have a population here that looks a little bit like the 80s. If you compare that to the Cytoflex that we have at dental school, it's a LX, you see that the profiles actually match each other. So you get a population that is 110, 110 stained and unstained. You get a massive population in the Cytoflex, which appears as well in the Astros, plus the noise that I mentioned before. And then you have the noise. Clearly, the Cytoflex is a very powerful instrument. You can see the sensitivity is very high, yeah? But you can get the same pattern in both instruments without completely unrelated, cuvette or jet in air. So we use the strategy of gating based on pulse width. If the pulse width allows you to distinguish a nanoparticle from the noise, why not to gate in the minimal value of pulse width and then look at the scatter values? And that is where the surprise came, that you can actually resolve the bottom end of the 80 nanometer particle from the noise by using a gate that is based on the minimum scatter value of width. And this is another layer of different particles that we're getting. So here you have the old events, the gray area will be everything. But when you get on the what I call the nano width, you will get essentially this to distinguish the bottom end of the 18 nanometer particles. Now, if you compare now the Apogee and the Cytoflex, acquire one after the other one, and you do the same nanoscale or nano width kind of gating, you get essentially this kind of rendering. In the Cytoflex mix, you get down to 80, 100 is shared by both big mix, and there is nothing underneath when you're talking about the Apogee below 100. And overlaying all the bits, you get something like this. These are the 100, These are the 80 that are disappearing from the apogee mix. And when you overlay all, this should be actually a contour plot. I probably exported the file in the wrong way, so now you're getting kind of shadow of colors. But the interesting thing is that when you overlay both set of bits, you get a lot of silica bits in the apogee bits, which is awesome. They are very closely related to the refraction index of EVs. Yeah, you get that the Astros not only distinguish 80 perfectly from noise, but also can distinguish roughly 80 from 100, and it can distinguish then different particles based on the refraction index and sizes, which is actually beautiful. It means illumination-wise, it's very consistent and very fine in terms of intensity rendering. And I'm getting now to the kind of point that is a kind of a mystery for me, and we are trying to find out why this is happening. But remember that I was using all the time the width of the nanoparticles to clear out my particles and my events from noise. Now, if you consider the Peter Doherty and the dental school Astros, we did both the experiments on it, you can see that the resolution in Peter Doherty is much better. You can see the rendering of the whole profile the dynamic range is larger. In the dental school is a little bit more constricted. You can still see something that looks like 80. When you do the gating based on the size scatter width, and you try to look at the fluorescence, you essentially see the 80 nanometers in the dental school not captured by this population here. Yeah? Something that I want to mention as well. Yeah? And for us was kind of puzzling that what is happening. Is this actually 80 nanometers? Why are you getting a disappearance of the particle from the noise? Now what we discovered is that it depends on what you're measuring. So if you're measuring size scatter and you're doing size scatter width, you can capture the particles down to the 80 nanometers. But if you capture now the forward scatter width, which is barely resolved, yeah, in the plots that we have, you essentially lose 100, you lose 80, you lose many of them. So where are the nanoparticles? Why I cannot get them in the smaller width profile? If you gate on the width profile that I have in the Astros, if you instead of gating on this only, you get each of these interesting patterns that you get in the noise and the width profiles, you see that the nanoparticles are actually, some of them, sharing properties of the noise in terms of width. Now, remember that this is an instrument that is a digital instrument. Post-processing is important, the definition of what is a pulse, what are the boundaries of the pulse, what is the baseline. The width, in the case of this instrument at least, when you're getting to the lower end and the lower end of detection, will confuse some of the nanoparticle pulses with the noise. That's what we thought. And that's what this suggests. If you take now the beautiful plot that I showed you before with all the particles captured, if I gate on the scatter plots directly without any gating, and I look at how each of the population appear in terms of balance between the nano width and the width that the particles are contaminated with the noise, you see that, yeah, the closer you are to the baseline, the closer you are to the noise, the more likely you will have some of these particles being confused with the noise in terms of width. And it happens with the forward scatter, it happens with the side scatter, and progressively as you go towards larger signals. This is very important. When you're dealing with nanoparticles and you want to consider measurements in height or area or width, what impact this hybridization will have in your area measurements? Yeah, the height seems consistent regardless of the particles being hybrid or true nanoparticles in terms of width. But what effect does that have on area measurements? So I took this case of a 200 nanometer particle with a minimum width and this signature of noise that happened to happen in the Astros. It's not random actually. So I wonder if it's something electronic related. But you take any of these cases and you look at what happened with the area and you find that the particles that have the minimum area are the ones that have the minimum width. And particles that have a width of the noise will increase roughly the area measurement, which means that I will never use the area if I'm measuring nanoparticles in the Astros. And we came up with this idea that sounds a little esoteric. When I mention this to people, they say, what? It's the idea that pulses can be confused and mingle with the noise. When the signal is very close to the noise, how the instrument knows where are the boundaries. And in the Astros, in the case of the Astros, you kind of get a kind of impression that the noise pulse is actually the pulse, is essentially the width of your actual measurement. So in that case, you will have a height that looks like the height of the nanoparticle, but the area will be higher than the area of a single nanoparticle with the minimum width, and the width clearly will be the width of noise. Larger signals will be fully distinguished, the boundaries will be set up, yeah? So to conclude the presentation, well, we have described briefly one of the examples of how we essentially go about when we try to optimize the scatter of the scattered alignment for the instrument, for the Astrios. We would like to essentially continue this and actually extend it to exosomes and extracellular vesicles. I don't think the full characterization is still yet. We're still trying to see what impact on this level of resolution. How can you break it down? We have already some results on that sense, showing that the instruments that we have the best, you can take it to be a worse kind of instrument as well, depending on how you play with things. We would like to play with all the lasers and measure scatter in all the angles, in all the wavelengths. We know that 561 is a very good laser for the Astrios in terms of nanoparticle resolution. We want to take it down. It's a little pushy, but we get a space between 80 and noise. We want to see what happens if you put 16 nanometer particles. I mean, this is already, in former times you will get burned by this anyway, because it's absolutely heretic, but it's happening actually, so why not to try even further? Sorting will be the aim, but we don't have many people actually doing EV sortings at the University of Melbourne at the moment, but we're trying to get some collaborators to get some samples. And the conclusions are these, based on the data that I'm showing you, the instrument have a beautiful capacity to resolve nanoparticles like I've never seen in my life. The instrument can do that and distinguish particles of different sizes. Still yet to know, I still to know how this relates to silica limits, because I'm talking about polystyrene limits. And the fact that I found that the instrument can resolve when you maximize the resolution, the nanoparticle from the noise based on pulse width signature. So you will not see that in many instruments actually. And this is something that you can use as a tool, not only to isolate your particles to get more pure and beautiful rendering of your profiles, but also to essentially increase your purities. You are sure that what you're counting is what you're seeing, because what you're seeing is actually clear of noise. And well, we have described these results of the hybridization, and still have to talk to Bellman Coulter to understand exactly how this happened. And it's something that I think can be corrected, because it might be actually something that the pulse processing can deal with. Thank you very much. Before that, I want to acknowledge all the people that work on this. So University of Melbourne, Tina Luke, Angela Jean, Catherine Lee, Lankesha Japa, they were essentially taking notes, helping me, aligning with me, trying to reproduce the whole procedure of alignment. Vanta Jameson, which is also the University of Melbourne for discussions. When I started getting these hybrids, I was getting nuts. So I essentially went to talk to people and see what they were thinking about this. From cytometry, Melbourne Cytometry group, we have Jessa, you have Michael Thompson, Matthew Wharton, Ralph Rossi. Many things have been discussed with these guys already. Yeah. Bellman Coulter Australia, Natalie Sanders, exclamation marks. She has been amazing. Many of these alignment steps were done in the presence of Natalie. Bellman Coulter also was very supportive, discussing and following up the results, and also they helped me with the beats that I use, the Cytoflex prototype beats. Now, something that I want to also, part of the disclaimer, is that we decided very early when we started getting these results not to share any method or information on how to get there. The idea was if you can get independently to the same result, well, you get essentially the knowledge of each method. And I think that's what we did. So I think up to now you haven't essentially have a full presentation of all the data combined. So thank you very much for all of you attending, and sorry that I took probably too long.